For this question, we want to solve the exponential equation 8 times 2 minus 10 to the 4x minus 3 equals 9. So the directions do say that this is an exponential equation, but we would know it's an exponential equation anyway because the variable is in the exponent. So when we solve exponential equations, we have three methods that we can rely on. We can rely on a method where we try to make the bases the same. So that would be b to the u equals b to the v. If we get it in that format, we can say that u equals v to solve. That's called relating the bases or using the one-to-one property. And then we have two other methods where one of which we have an exponential equation and we're going to convert it to a logarithmic equation. That would be log base b of x equals y. I've got that backwards, I apologize. It's log base b of y equals x. The log always equals the exponent. And then we have a third method where if we start with an exponential equation, we can take the log of both sides, natural log on the left and natural log on the right. So this method right here requires that the bases be the same, and these two methods you can use almost any time you have exponential equations. But what I want to point out to you guys is that all of these strategies for handling exponential equations have the exponential part isolated on one side of the equation. So in all of these cases, we need the exponential isolated on one side of the equation before we use the strategy. So in this example, our exponent is 4x minus 3, and 10 is the base of that exponent. So before we can start implementing these strategies, we want to isolate that portion of the exponential equation. So to do that, I need to get rid of this 8. This 8 is multiplied. And so I'm going to do the opposite, which is to divide. That's going to give 2 minus 10 to the 4x minus 3 equals 9/8. And I still need to isolate that exponential, so I need to get rid of this 2. So I'll subtract 2 on both sides. That gives negative 10 to the 4x minus 3. And I'm going to combine these together. So let's rewrite 2. 2 is 2 over 1, and I want a denominator of 8. So I'll multiply by 8 over 8 to get negative 16 over 8. We're going to leave 9/8 the same, and now we can add those together. So a positive 9 and a negative 16 would be a negative 7 over 8. And I still want to isolate this exponential. I need to get rid of that negative, so I would divide by negative 1 on both sides. And I'll continue writing over here. We have 10 to the 4x minus 3 equals a positive 7/8. So we have isolated the exponential on one side of the equation, and now we can start to think of these strategies that we wrote down. Now when we look at the bases, I have a base of 10 and a base of 7/8. The first method of relating the bases requires us to have the same base on both sides, so we're not going to be able to use that method. But we will be able to use one of these other two methods. So let's give the second one a try, where we take the log of both sides. I'm going to do natural log on the left and natural log on the right. This is something that we're allowed to do because exponential and logarithmic functions are one-to-one. So once we take the log of both sides, we now have the log properties available to us. And one that we're going to use is called the power rule for logarithms. That allows us to take that power and make it the coefficient on the log. So we have 4x minus 3 multiplied by natural log 10 equals natural log of 7/8. I'll use the distributive property, and I'll distribute this natural log of 10 to both terms inside the parentheses. That's 4x natural log 10 minus 3 natural log 10 equals natural log 7/8. And now I only have one x. I want to isolate that x. So I'll add 3 natural log 10 on both sides. That's 4x natural log 10 equals natural log 7/8 plus 3 natural log 10. And now I can isolate that x by dividing by 4 natural log 10. So I'm left with x equals natural log 7/8 plus 3 natural log 10 over 4 natural log 10. So let's practice typing this answer in our calculator. So here's our calculator. Let me clear these buttons so we have a fresh start. And I'm going to put parentheses around my whole numerator because there's multiple terms and we need to help the calculator know what order to do the operations in. So that big fraction bar is a natural grouping of the whole numerator. So we're going to put the grouping symbols around the numerator to make sure the calculator knows. So we have natural log of 7/8 plus 3 natural log of 10. We need to close parentheses for the numerator. And we're going to divide. I'm going to put parentheses around the whole denominator. Once again, we need to do this to make sure that we're dividing by the whole denominator, 4 natural log 10. If we don't put parentheses, the calculator will only divide by 4 and then multiply by 10. So we want to divide by 4 natural log of 10. We're going to close parentheses for that log and close parentheses for the denominator. And we get approximately 0.74 if we round to the nearest tenths. For this question, we want to use the properties of logarithms and the logarithmic property of equality to solve the logarithmic equation. So there are two main strategies for solving log equations. We've already listed here the property we're going to use, but I just want to compare the two methods that we typically see for solving log equations. So with log equations, one property we use is this property of equality, and that says log base b of m equals log base b of n. So what you see is a log with the same base on each side. And by this property of equality, we know that what's inside of the logs must be equal to each other. So it allows us to simplify the log equation. The other strategy is to start with a log equation and convert it to an exponential equation. So that does not require you to have logs with the same base on both sides. So we might only have the log on one side. And if you have this situation, you can convert it to an exponential and have b to the y equals m. That takes the log out of the equation, and then you're able to solve what you have remaining. So sometimes if you know those two strategies, you can use what you have in the problem to give you clues on what to do. So I notice that I have a log on the left and logs on the right, and so that indicates to me that I want to use this strategy because it has logs on both sides, logs with the same base on both sides. But before I can use that property, I need to have the log being isolated on one side of the equation, meaning there shouldn't be anything multiplied or added onto the log. So we have some cleaning up to do before we're able to implement this property. So what we're going to do is we're going to use some properties of logarithms. And there's two that we're going to use in this problem. One of them is the power rule for exponents. And the power rule for exponents deals with this situation where you have log base b of m to a power. And anytime you have a power and an exponential expression inside the logarithm, what you're allowed to do is you're allowed to take that exponent, that power, and move it into the coefficient. So you can write this as that power times log base b of m. Now, we're actually going to go the other way. We're starting with the right-hand side of this equation. We have a coefficient on the front of our log. I'm going to highlight it over here. So we have a coefficient of 2. And we're going to put that power, we're going to put that back into the exponent, back into the power. So that's one property we're going to use. On the other side of the equation, I notice I have addition here. And we're going to use a property called the product rule for logarithms. And the product rule for logarithms has log base b of m times n. So we have a product within our log. And we can write that as log base b of m plus log base b of n. And so you'll notice that addition on the other side. So we're going to go the other way. We have addition, and we're going to turn that into a single log with the product on the inside. So let's write our problem out and work on this example. We have 2 log of x plus 3 equals log of 8 plus log of 2. So we'll use that power rule for logarithms to move that coefficient of 2 into the power. So the left-hand side becomes log of x plus 3 squared. On the right-hand side, we're going to use that product rule for logarithms, where we can write it as a single log, and we're going to multiply what we have inside the log, so that's 8 times 2. So on the right-hand side, we have log of 16. And I'll copy down the left-hand side, log of x plus 3 squared. So now we have written each side with a log with the same base. In this example, no base is written, so we assume the base to be 10. So we're able to use this property of equality now, which says that the expression inside the log on the left, x plus 3 squared, is equal to the expression inside the log on the right, 16. So now the logs are gone and we're able to solve the equation that's remaining. So this is a quadratic equation. I'm going to get rid of the squared by square rooting both sides. The square and the square root cancel each other out, leaving me with x plus 3. I forgot the square root over here, square root of 16. We get plus or minus 4. And now I want to get x by itself, so I subtract 3. That gives x equals negative 3 plus or minus 4. So we've got two answers. Negative 3 plus 4 would be 1, and negative 3 minus 4 would be negative 7. Now, before we're done with this problem, we do need to check our work. Logarithms have restricted domains. Log of a negative number is something that is undefined. Log of 0 is undefined as well. So when we check, we have to make sure that the solutions that we came up with are in the domain of our logs we have in the equation. So let me zoom out just a little bit so we can check. And we're going to check our solution of 1. We're checking x equals 1, and we're going to substitute that into the original. That's 2 times the log of 1 plus 3 equals log 8 plus log 2. And so what I'm checking is that we have a positive value inside the log to make sure that it's defined. 1 plus 3 is positive, so we're going to be able to keep that solution of x equals 1. Let's try the other solution of negative 7. And if we substitute that in, we have log of negative 7 plus 3. And negative 7 plus 3 is going to be a negative value. And log of a negative is undefined, so we have to throw that solution away. So the only solution to this equation is x equals 1. For this question, we want to use the properties of logarithms to rewrite the given expression as a single logarithm. Whenever possible, evaluate the logarithmic expressions. So in this example, we have log base 9 of x plus 1 minus log base 9 of x plus 7 minus log base 9 of square root of 3x. So in this example, we want to condense into a single logarithm, and we have a few properties that we're able to use to do this. We have the product rule, and the quotient rule, and the power rule. Now we're trying to condense to a single logarithm, so we're starting with multiple logarithms, and we're trying to condense to a single logarithm. So we're going to read it starting with the right-hand side and try to simplify to become the left-hand side. On the right-hand side, you can see that we have the sum of two logs. And when you have the sum of two logs, you can condense with multiplication. Our problem has subtraction in it, so we're not going to use that property. We're going to use the quotient rule, which has subtraction. And when you have subtraction of logs, you can condense into a single log using division. And we notice that this first log, the first term is positive, and inside the log is what goes in the numerator. And the second term is negative, and what's inside the log goes into the denominator. So we're going to be using this property here to condense. The last property is the power rule, and we use that whenever we have a coefficient on the log, and that coefficient will become the power on the inside of the log. We look at our example and none of our logs have a coefficient, so we don't need to use that property. So it looks like we're only going to be using the quotient rule for logarithms. So let's rewrite the example so we can have it a little bit larger. We have the log base 9 of x plus 1 minus log base 9 of x plus 7 minus log base 9 of square root of 3x. Now it's important to notice that all of these have the same base, and that is required in all of our properties to have the same base so that we can condense to a single log. So I'm going to condense this to a log base 9, and this term, this log term, has a sign that is positive in front of it. No sign is written, so we assume it to be positive. And so when I condense, that x plus 1 will go into the numerator. When I look at the next term has a negative in front of it, and that factor will go into the denominator, x plus 7. And then we have our last term here, which is also negative, and that term will go into the denominator, square root of 3x. So I've written that a little bit bunched up. Let me try to write it nicer for you guys. It's log base 9 of x plus 1 over square root of 3x times x plus 7. And I'm looking at this to see if I can do any simplification, and I don't see any obvious simplifications, so I would stop here. You could also write this as log base 9 of x plus 1 over x plus 7 square root of 3x. That would be acceptable as well. For this question, we want to find the domain of the logarithmic function f of x equals log base 5 of negative 8x. So when we're looking for the domain of a logarithmic function, we need to know when a log function is defined. So a log function, log of something, will only be defined if what's inside the log is positive. So this is defined, but log of a negative is undefined, and log of 0 is undefined. So we can sort of understand this a little bit better if we know the meaning of a logarithm. A logarithm means an exponent. So if we have log base 3 of 9, we say we don't know what that equals. So we'll say that equals p. Then that is 3 to what power equals 9. And that's 3 to the second power. So if we have a positive value inside here, this definition of a log being an exponent makes sense. But if you have a negative in there, log base 3 of negative 9, 3 to what power equals negative 9, this doesn't make sense. You can't take a positive number and raise it to a real number and get a negative answer. And the same thing happens with 0. Log base 3 of 0. 3 to what power equals 0? Once again, it's not possible to take a positive number and raise it to a power and get 0. So a log function is only defined for positive values. So if we want to find the domain of this log function, we need what's inside of the logarithm to be positive. So we're going to create an inequality that says negative 8x, that's the expression that we have inside of our log, needs to be positive, which is greater than 0. And we're going to solve that inequality. So I'm going to divide both sides by negative 8. And with inequalities, when you divide by a negative, you need to reverse the inequality symbol to maintain the truth of that inequality. On the left-hand side, the negative 8 divided by negative 8 becomes 1, and 1 times x is x. And on the right, 0 divided by negative 8 is 0. So we can say that all x that is less than 0 are in the domain of this log function. So if we think of that on our real number line, we would mark 0 with an open circle to not include it, and shade all of the values less than 0 to the left of 0. And we usually represent domain in one of two ways. You can represent it in what's called set builder notation. So that's x, all x, such that x is less than 0. Or you can represent it very similar to the number line in interval notation. And you're going to choose a lower bound and an upper bound. That's negative infinity to 0. So we do that to match the shading on the number line. So our domain in interval notation is negative infinity to 0. For this question, we want to use the graph of y equals 3 to the x and transformations to sketch the exponential function below, f of x equals 3 to the negative x plus 3. In addition, we want to determine the domain and the range, and the y-intercept and the equation of the horizontal asymptote. So I'm going to start by taking a look at the graph of y equals 3 to the x. We're going to sketch the graph of y equals 3 to the x by plotting points. I'm going to choose a standard set of x's, negative 2, negative 1, 0, 1, and 2. And we're going to substitute it into that equation y equals 3 to the x. So let's start down here with the easy ones. 3 to the first power is 3. 3 to the second power is 9. 3 to the 0 power is 1. 3 to the negative 1 power. Having a negative in the exponent means reciprocal of the base. So the reciprocal of 3 is 1/3. And the power is a 1, so that's 1/3. And we'll do the same thing here. 3 to the negative 2. Having a negative exponent means reciprocal of the base. That's 1/3 squared, which is 1/9. So this gives us a set of ordered pairs, negative 2 and 1/9, negative 1 and 1/3, 0, 1, 1, 3, and 2, 9. And we can get a good sketch of the graph with these 5 points. So negative 2 and 1/9 would be really close to 0 for the y part, negative 1 and 1/3, and 0, 1. 1, 3, and 2, 9. These points connect with each other in a very smooth curve, and we can follow the pattern of what's happening. So if we continue to choose larger x values, the y values become larger. And on the left-hand side, if we continue to choose negative x values, then our y values will continue to get closer and closer to a y value of 0. So for this function, we have a horizontal asymptote that's falling right on top of the x-axis, and that is the line y equals 0. So this is considered our base graph of y equals 3 to the x, and we want to use that information to help us draw the graph of f of x equals 3 to the negative x plus 3. So we're going to graph that function with the idea of transformations. So we're taking a look at the function f of x equals negative x. Let me write it out here. F of x equals negative x 3 to the negative x plus 3. So we identify the base graph as being 3 to the x power. That's the function that we just drew. Y equals 3 to the x. We want to keep in mind that we have a graph that's increasing and that horizontal asymptote right on top of the x-axis. That's going to be very helpful when we try to graph with transformations shortly. So we have two transformations in this function. We have a negative and a plus 3. We have a negative and a plus 3. So the negative, multiplying by a negative, is the transformation of reflection. And there are two types of reflection, a vertical reflection and a horizontal reflection. When you have a negative that's multiplied onto the x part, that's on the inside of your base, that is a horizontal reflection. So this is horizontal. If the negative would have been here, this negative is on the outside of the base function, and that would be a vertical reflection. The plus 3 is a shift. When you add and subtract onto your base, you have shifts, and you could have a vertical shift or a horizontal shift. And because this is adding out on the outside, adding to the overall base, this is a vertical shift, and because it's a plus, it's going to shift up. So this is going to help us draw the graph. I'm going to try to zoom in so my graph isn't so small here. So we're going to take these points, and we want all of these ordered pairs that are on the base graph. We want to reflect horizontally and then shift up vertically. When we reflect horizontally, that's affecting the x, and when we shift up, that's affecting the y. So when we think about these ordered pairs that we have, the reflection will change only the x coordinate, and it's going to change it by being the opposite. And then the second transformation will only affect the y, and it will add 3 to those coordinates. So I'm thinking of those ordered pairs that we have. -2 and 1/9, that point will change the x to the opposite, +2, and the y, we're going to add 3, so it'll be 3 and 1/9. The point -1 1/3 will have the opposite x and add 3, so 1/3 plus 3, 3 and 1/3. So that's what it will transform to. The point 0 1, well, the x is 0, the opposite of 0 is still 0, and if you add 3 to 1, you get 4, so that point will move to 0 4. The point 1 3 will become the opposite x and add 3 to 3, and you get 6. And then the point 2 9 will be -2, the opposite x, and add 3 to get 12. So if we keep those points in mind, in addition, the horizontal asymptote is at 0. We're going to shift that up 3, so it's going to move to be at y equals 3. And so we get a new graph that looks something like this. -2 and 3 and 1/9. Oh, that's a +2. And 3 and 1/9 would be about right here. +1, 3 and 1/3 would be about here. 0 4 and -1 6 and -2 12. So we get this picture. Let's zoom out so we can see the base graph and this transformed graph. So you can see the graph is horizontally reflected. So what's on the left becomes the right, and what's on the right becomes the left. And then shifted up 3, so the entire graph is shifted up to this line right here. So we have the new graph, and we have a couple more questions about this. Let me zoom out to the directions. And in the directions, we want to find the domain and range. The domain of every exponential is all real numbers. The range, because we've shifted up 3, becomes 3 to infinity. We've already noticed that the horizontal asymptote is y equals 3 because it was shifted up 3. And you can do the calculation for the y-intercept, but it is 0 4. So let's do the calculation. Our function is 3 to the -x plus 3. If we're looking for a y-intercept, we let x equal 0. And that's f of 0 equals 3 to the -0 plus 3. -0 is 0. 3 to the 0 is 1. And 1 plus 3 is 4. And so we get the ordered pair 0 4 being the y-intercept. On this question, we want to solve the exponential equation. 4 to the 4x minus 1 equals 15 to the x plus 1. This is an exponential equation. We know it's an exponential equation because we have variables in the exponent. We have three main strategies that we use for solving exponential equations. And I want to take a look at them before we start solving this problem. So the first one, your book calls relating the bases, and other places call it the one-to-one property for exponential functions. So this method requires you to have the same base on each side of the equation, and then you can simplify by setting the exponents equal to each other. If you look at our example, we have a base of 4. You could change that to be a base of 2. 4 is 2 squared. However, the other side is a base of 15, and there's not really much we can do to change the base on this side because it's not a base to a power. So the first method will not work for us because we're not able to make the bases the same on both sides. And then we have another strategy which we convert to a logarithmic equation. Exponents and logarithms are inverses of each other, and we can write equivalent equations in either form. So if we have an exponential equation, y equals b to the x, we can write that as a log equation, and it's still a true statement, log base b of y equals x. So this is an option for us in solving this equation. Another method is to take the log of both sides. This is something we're allowed to do because both logs and exponentials are one-to-one, and so when we take the log of both sides, we get an equivalent statement. So with this method, we have y equals b to the x. We take the log of both sides. We apply the power rule for logarithms to get the variable out of the exponent. And then we solve for the variable by dividing both sides by natural log b, and we've solved. So what I'm going to do is I'm going to show you how to solve this problem with both methods, and we'll see that you do have the choice between doing it either one of these ways. So let's start with converting to a logarithm. Now this is an interesting problem because you actually have two bases, a base of 4 and a base of 15. So you can choose which base you want to use. The base of the exponent becomes the base of the log. So let's choose a base of 4. So if we're going to write this as an exponential, you would write log, excuse me, I said that backwards. We're going to take the exponential and write it as a log. We're going to write the word log and use base b. The log always equals the exponent. You've got two exponents here, but you want to use the exponent on that base. So since we use base 4, we're going to set this equal to 4x minus 1. And then the other side of the equation is what goes inside that logarithm. So that's 15 to the x plus 1. Let me rewrite that so that it's not so messy. Log base 4 of 15 to the x plus 1 equals 4x minus 1. So now we can use the power rule for exponents, power rule for logarithms, and move this exponent into the coefficient. So this becomes x plus 1 log base 4 of 15 equals 4x minus 1. Then we can use the distributive property and distribute this log to both terms. That becomes x log base 4 of 15 plus log base 4 of 15 equals 4x minus 1. Now we want to solve for x, and we have x's on both sides of the equation. So we're going to group the x's to one side and all the terms without x to the other side. So I'm going to move this to the left so that the x's will be on the same side. And these two terms don't have x, and I want them on the other side, so I'll move log base 4 of 15 to the other side. So this would give the equation x log base 4 of 15 minus 4x equals negative log base 4 of 15 minus 1. I can now factor out the x that we have in common. That's x times log base 4 of 15 minus 4 equals negative log base 4 of 15 minus 1. And now I can isolate x by dividing both sides by log base 4 of 15 minus 4. Log base 4 of 15 minus 4. So we have our solution being x equals negative log base 4 of 15 minus 1 over log base 4 of 15 minus 4. We're going to do this problem with the other method as well, and then I'll bring my calculator out, and we're going to show that these two are equal to each other. So let's write our problem down again. We have 4 to the 4x minus 1 equals 15 to the x plus 1. And this time I'm going to solve it by taking the log of both sides. So I'll do the natural log on the left and the natural log on the right. And on both sides, I'll use the power rule for logarithms to move that exponent into the coefficient. That becomes 4x minus 1 times natural log 4 equals x plus 1 natural log 15. And then I'll use the distributive property on the left and use the distributive property on the right. So this becomes 4x natural log 4 minus natural log 4 equals x natural log 15 plus natural log 15. Once again, we want to group the x's to one side and the terms that don't have x on the other side. So we'll move this term that has x to the left, and we'll move this term that doesn't have x to the right. That gives 4x natural log 4 minus x natural log 15 equals, and on the other side, we're going to have natural log 4 plus natural log 15. I have a common x, which I'll factor out. That gives 4 natural log 4 minus natural log 15 equals natural log 4 plus natural log 15. And I can divide both sides by what's in the parentheses. And that's 4 natural log 4 minus natural log 15 on both sides. And I have my other solution, x equals natural log 4 plus natural log 15 over 4 natural log 4 minus natural log 15. So let's get our calculator out and type to see if we got the same answer. So I'm going to type in, I'm going to start with the one on the bottom right because that one's a little bit easier to type in. I need parentheses around the numerator. That's natural log of 4 plus natural log of 15, close parentheses for the numerator, divided by, and we need parentheses around the denominator. 4 natural log 4 minus natural log of 15, and close parenthesis for the log and close parenthesis for the denominator. So we get 1.44 for this one. Now let's try the other one. So the other one, we need parentheses around the numerator again. Negative log base 4. So we're going to go, I think the trick was math alpha math. Yeah, okay. Log base 4 of 15 minus 1, close parentheses, divide. We need parentheses for the denominator. We're going to do math alpha math to do log base 4 of 15 and we want a minus 4, and we'll close parentheses for the denominator. And you can see we get the same answer with both methods, 1.44. Thank you for checking out my videos. Have a great day.